All right. Well, thanks. Thank you to Yuval, Sumathi, Subhro, and who else? Ganpathy. Sorry, the man. I know. I mean, it's disaster. I'm not going to hear the end of it. Thank you. And well, I'm going to talk about something a little different from what Mandar has just talked about. He was looking at a high magnetic field. I'll go for zero magnetic field in most of the experiments, except the last part, which we will use a magnetic field to identify certain new phases. Now, my group in Institute of Science in Bangalore, over there, we work on various kind of systems, but of course, given today's topic, I'm going to look at specifics of graphene and around its boundaries in different forms. I'm going to come in the very next slide. But it has been possible because of a large number of excellent quality of students and my collaborators within the institution. There are people from different institutes, not just in IISc, not within the, just within India, but outside as well. Most of the work has been published, but I'm going to actually talk a little bit about something which is unpublished, actually last 20–30% of my talk today, because I'm really excited by new possibilities of or phases that can emerge at the boundary of graphene, because of either interaction or plane defects. We do not know the answer. Maybe something will emerge through this talk. Okay. I'm going to talk about 3 different cases today. The first one is relatively old, which is what happens at the edge of a single layer graphene. The second one, I'm going to talk about the edge of a bilayer graphene, which is gapped, and you can actually get a marginal topological behavior. I'm going to give you some form of account of how we can experimentally detect these phases. And then, of course, the third one will be, again, a boundary, but this is not a boundary at the physical boundary, but a boundary of a grain of graphene. And I believe there are very interesting physics at those grain boundaries that we need to still understand. My talk will be primarily using new experimental techniques to understand the phases or the states of electronic states at the boundaries like this or like this. What Mandar showed you earlier was primarily determined by the current voltage characteristics or plane resistivity as a function of temperature or magnetic field and so on and so forth. I will go one step beyond that, and I'm going to show you how using electrical noise can become a very interesting and powerful experimental tool to give you information about these particular states. Okay? Okay. First, to give you a little bit of background of what happens here is that a band structure of graphene is probably very well known. Everybody here knows about it. If you take an infinite layer, then it's a conical band structure with a density of states that varies linearly as a function of energy. The boundary of graphene, that's, so for example, if you take a look at, so this is a, if I take the zigzag edge of the boundary of graphene, if you take a simple tight binding model, you will see that there are zero energy edge states over here, which is not there in the armchair edge. There is no topology involved here. Plain and simple tight binding model usually gives this. And as a result, if I look at armchair edge, the band structure has a gap in its at k equal to 0, whereas if you take the zigzag edge like this, there is a zero energy state which is, can go from somewhere around pi/3 to the Brenner zone boundary. As a result, over here, even for extremely small Fermi energy, you will always get a state which is dissipationless, or if your edge is perfect zigzag edge, you should get a perfectly conducting electrical channel along the grain boundary, along the boundary of graphene. Okay, so this has been a question for a while now. Theoretically, this was predicted significantly a long time back. This is 2007. So this is overall the zero energy state, and if you have Fermi energy somewhere here, you get this exactly 2 states, one going around this side and other one going along this direction, gives you the perfectly conducting edges. Okay, And if you have got a perfectly conducting one-dimensional mode, the conductance is 2 square by h. That is also a purely non-interacting physics that comes up. However, there have been theoretical work where you take into account the strong Coulomb interaction at the edges, and there still seems to be some form of controversy exactly how much the on-site interactions will be and what their effects are. But there has been more or less, there are several experimental reports, for example, this one in 2014 in Nature, which shows that if you include the Coulomb interaction, now you can have a magnetic order of the two edges. Either it's antiferromagnetic or ferromagnetic, depends on the width of the ribbon which is separating the two edges. Okay. Experimentally also, people have tried to look at the edges, but primarily through spectroscopic techniques. This is some work done by Mike Chromius group, which is essentially a STM, scanning tunneling probe, and look at the bright line along the edge of, this is the carbon nanotube, which is cut along the length and made a ribbon out of it. So you can see the edge states are essentially giving you a strong additional feature at the edges. After that, again, STM shows there is a magnetic order, and that is probably because of strong Coulomb interaction along the edges. Okay, and as a function of the width, you can either have a antiferromagnetic order, or you can have a ferromagnetic order, almost like a first-order phase transition. Right, we'll come back to that. However, unlike the case of a single-layer graphene, bilayer graphene is a different beast altogether. Now you have got two layers, and hence you have got an additional degree of freedom, which is a layered degree of freedom. And as a result, you have a very similar to Dirac equation. However, there is now a mass, which is why the bilayer graphene is called a heavy, Dirac's fermions over there. And also now you have a Berry phase of 2 pi. An interaction between the two layers gives rise to this additional mass. How does it become a topological insulator? Can be explained very simply with a cartoon. Let me just explain to you. Suppose you have got two graphene layers like this, and assume that there is no interaction between the two, then which we have essentially a two conical band structure of individual graphene layers. Suppose I apply an electric field perpendicular to the plane of bilayer graphene, and in which case the two conical bands essentially shift vertically with respect to each other, something like this. Remember, I still do not have any coupling between the two. I only have an electric field which is separating the two and essentially creating two voltages. The two layers are in two opposite, different voltages. And then I switch the interaction between the two layers on, something like a coupling, and now you can see that there is a little bit of band inversion that takes place. So this is a valence band-like structure, and this is a conduction band-like feature. And you have, in case of finite electric field, the small gap bilayer graphene is some form of a topological insulator. If you increase the coupling really strong, then you are essentially ending up with a topological insulator-like band structure. The difference between this and other normal topological insulators, there's no spin-orbit interaction here, and the topological protection is given by the valleys. Okay, so it's a valley symmetry that protects the time river. Yeah. This is primarily the interlayer interaction. Yeah, that's right. So the hopping integral, this T lambda is the hopping integral between the two layers. Okay. Right. So this has been now used in valley Hall insulating phases, and various many experiments. There have been valley dissipation-free valley currents that have been generated. This is from Penn State, from I guess from Jinju's lab, and there are several now experiments which uses this unique topological feature of gapped bilayer graphene in this kind of playing with valley current and edge currents. Okay. You can do the same thing even in case of a single layer graphene. For example, if you put a single layer graphene on a boron nitride structure, because the boron nitride are B and N, the boron and nitrogen are different chemical species, they break what you call the mirror symmetry, in plane mirror symmetry, and that leads to value Hall effect even in single layer graphene. And as a result, you can see that very strong non-local structures in case of single layer graphene, which is kept on boron nitride. The difference between the standard topological material, which is protected by spin orbit interaction, and this one is because in case of bilayer graphene or single layer graphene, the edge transport is strongly dependent on how good your edge is. Until and unless you have purely zigzag edge, for example, you will not get the kind of experimental features like E square by H of conductance in graphene of this sort. As a result, you can see that as you make the sample size, the length, longer, the topological features are essentially decreasing in an exponential manner, which makes it particularly difficult for detecting in most experiments. Okay? So this is what we had been looking at, that how we can look at possible topological order along the edges using transport of different type. Okay. So this is the experimental challenge. One is the edge is almost always not perfect. And the second is, in the case of single layer graphene, for example, you have the edge conduction and bulk conduction happening parallelly. So it's very difficult to separate out one from the other. And finally, of course, how will you detect the exact one-dimensional nature of transport? Okay, so these three are usual experimental challenges. Let me just go through it. Many groups have been trying. This is from IBM group, and also these are experiments which were done. This is the Groningen group result. These are old work. They wanted to look at the edge transport, but it was not particularly clear because the bulk transport was shunting the edge quite heavily. Okay. So what did we do? This is an old work. I'll go very quickly through it. What we did, we tried to use an idea of, which came out in Science some time back, in which we wanted to have a wedge-shaped transport. Suppose you have a pure graphene like this, which is semi-infinite in nature, but if I create a wedge like this of 30-degree angle exactly, then I have zigzag edge on one side, I have an armchair on the other side. This is gapped because armchair edges are they don't have zero energy states, whereas edge states on the zigzag one has. So you have, in this region where the quantum confinement is very strong, the bands are, there is a gap over here, this is quantum confinement gap. However, the edges will conduct in this direction, and if you apply a battery between the two, then you should get electrical conductance of 2e squared by h. That was the idea behind our experiment that we tried to do. So how do we create edges or wedges like this, which has exactly 30-degree angle along the graphene length? Turns out that we don't have to do anything, and it's Mother Nature which allows you to do this. If you simply take a layer of graphene and physically tear it, and and take it apart, it turns out that in most graphene cases, the tearing happens along crystallographically symmetric orientations of facets. Okay, and this was one of the early results of, again, this was probably, I think, Mike Cromie's or Alex Zettel's group. Essentially, they fired electron and tore graphene inside a tunneling, TEM, transmission electron microscope, and saw extremely beautiful long-range order in the edge structure. Okay. So we wanted to use that. And we did it inside a scanning electron microscope. We created a robot and essentially tried to tear graphene inside underneath the SEM. While tearing, we wanted to look at the electrical transport through the system. And this is roughly what it looks like. So this is a tip which goes and tears graphene underneath the SEM, the scanning electron microscope. Again, very quickly, this is how it looks like. This is where the tearing is taking place. You can see this is the contact between the graphene and the substrate underneath, and you can see that when there is a huge contact area, the conductance is very large. If you tear farther, the contact area is decreasing, and conductance is decreasing too. This is the conductance of this point contact over here. Farther you go, this is where the contact area is extremely small. It's less than 5 nanometer, which is, according to quantum confinement, the electrical transport through this region will be extremely small. Should have been insulating, but instead what we are seeing, the conductance is essentially saturating towards exactly 2 square by h. And then when you pull it up so completely, you can see it has been, this contact has been detached, and you essentially have a drop in resistance or conductance, and the system goes into the insulating phase. Again, as I said, we looked at those regions of exfoliations, and they are exactly 30 degrees, showing that by natural tearing of graphene leads to extremely symmetric structures, mechanical structures. This was at that point of time, so this was done about November 2017. We didn't know that, but afterwards there had been several theoretical work which shows that this probably is a natural thing to happen. Okay, so then, and this is some, most of the tearings happen along the 30 degrees or 60 degree angles, which was very interesting in my opinion at that point of time. So you can see even at room temperature, we have got very strong quantum confinement, and we see conductances of E square by h. At low temperature, we get series of them. If I put all of them together, there's something really interesting that we see peaks at 2 square by h integral multiple. However, something very interesting over here is that in addition to 2 square by h, these are non-interacting peaks, we see another very strong feature at half 2 square by h, which probably indicates that the electrical conduction along the edges, or edge conduction, is spontaneously spin polarized. This is something which we will come back a little later. Okay, I'm going to move to the, so this is something which we did a little bit of DIDV characteristics, which is essentially the low energy density of states, and you can see a small gap opening up at low temperatures, probably saying that the edge conduction along the graphene zigzag edges is determined by the strong Coulomb interaction. Okay, my colleague Manish Jain's group did some in-field study, and this showed that typically the U by T is in the order of quarter, 0.25, to explain the kind of dips that we see experimentally. Okay, I'm going to move to the next one. So this essentially is a work which showed the edge of a single layer graphene, but then we wanted to look at and ask the same question for bilayer graphene in its gapped state. Okay, this was a work done by Amer, who is now a postdoc with Dmitry Efetov at ICFO. And we wanted to look at, okay, if I have bilayer graphene and I gap it, what kind of electrical transport is it? Is it a transport that happens along the two-dimensional insulating gapped phase, or it's actually, because of its topological nature, the transport occurs through the edge of the bilayer graphene? So for those who are, I'm not going to details of the experiment, but this is roughly how it looks like. You have a bilayer graphene, then you put electrical contacts, and then there are two insulators. One insulator is on top, other insulator is the bottom, and there are two gates, one on top, and that's called top gate, and one at the bottom, this is called a bottom gate, of course. And we can apply an electric field across these two gates to make the bilayer graphene insulating in nature. That's open a band gap in the quasi-particle energy spectrum, okay? On top of that, I can use electrical contacts to make the two graphene, the distance between the graphene, distance between the contacts vary. As a result, I can vary the length of my system. Okay, this is how a typical device looks like, okay? Typically, the length between two contacts is somewhere around 0.1 to 0.6 to 20 micron. I'll come back to that later again. So if I apply electric field between the two gates, one on top and at the bottom, then I open a band gap up, and as a result, the electrical conductance goes down. If I look at this particular structure, there are a lot of things there. Let me just break it up for you. So for example, over here, this trace where I have varied the bottom gate while keeping the top gates, I varied the bottom gate while keeping the top gate constant. This is the region where there is no gap at all in the quasi-particle spectrum. As a result, the conductance at the charge neutrality point, this dip is where the charge neutrality point is, the conductance at the charge neutrality point is very high. However, if you come here or you come here, this is where there is a band gap because of the electric field that has been generated between the top gate and the bottom gate. Here you can see the bottom gate is at minus 50 volts and the charge neutrality is attained at plus 15 volts. That depends upon the capacitive ratio between the top and the bottom gates. As a result, there is a huge electric field across the graphene, which results in much smaller conductance. Similarly on this side as well, because of the fact that the back gate is kept at 32 volt, you need a negative volt on the top gate to attain the charge neutrality point. As a result, the electric field is large, which is opening a band gap, leading to a very small electrical conductance at the charge neutrality points here. Okay? The experimental difficulty to understand the insulating state transport is both gapped, the bulk is gapped, so it's insulating, but at the same time, if there are edges along the boundary, edge states along the boundary, because of the fact that the edges are not perfectly zigzag in a normal exfoliated sample, we do not know whether this, the conduction is primarily along the edge. Okay? As a result, for a long time, the insulating state transport in case of bilayer graphene was assumed to be a two-dimensional insulating state transport. However, recently in 2017 or so, Manchester group came up and did this very interesting experiment using a superconducting interferometry where two superconducting contacts were used across a gapped bilayer graphene, and it was found that probably the majority of the transport in the insulating state occurs along the edge rather than through the bulk. And that was detected by using interferometry of the two supercurrent channels that go around the edges. Okay? And using some form of an interferometry which looks like a double slit interference pattern. However, the problem with this experiment was it was not shown to sufficiently low or sufficiently large band gap in the bilayer graphenes. And also, there could be other problems associated with the supercurrent spectrometry. So we wanted to ask the question that can we say how the electrical transport occurs in strongly gapped bilayer graphene? Well, one of the questions, the idea behind the experiment was very simple. You see, if I have a large number of localized states and my Fermi energy is in the localized state somewhere, then electrical transport occurs through hopping. It goes one state to the other and eventually it escapes from the source to the drain. Now, if it's a two-dimensional system, if I change the Fermi energy slightly, okay, it goes through a series of different set of localized states, and as a result, as a function of Fermi energy, the conduction starts becoming very, very noisy. However, it's not noise in the normal sense of noise, but it's a repeatable pattern of electrical conduction as you change the Fermi energy through a set of localized states. Okay? Now, if you make the system larger and larger, the number of possible states available to you to go through becomes more and more, scales as, in a two-dimensional case, scales as L square. And as a result, if I take this particular quantity, any quantity x, which in our case log of conductance, because it's a transmission probability in the localized regime, then in 2-dimension and 3-dimension, this is a self-averaging quantity. That means if you make the system larger, eventually the variation in conductance is going to become smaller and smaller. Great, but that is completely different from what you would expect in a one-dimensional system. The reason behind it, suppose you have a one-dimensional system, so this part of the sample is simply not allowed for you to access in any form. The conduction is always going to be dominated by the largest barrier in the channel of one-dimensional transport. If you have got a strong disorder, there is no way the electron can avoid it. So it's unavoidable hopping that determines the conduction in a purely one-dimensional system, and that is why one-dimensional system transport are intrinsically what you call non-self-averaging. You can make it longer and longer, but it's still the same bad region that's going to make the transport completely, will determine the transport, and hence it's non-self-averaging in nature. So we want to ask that simple question that is localized state transport in strongly gapped bilayer graphene a self-averaging transport? Okay? Because we want to see if there are edge states that's dominated. Yeah, sure.
I mean, if you have a really strong disorder, the distribution of barriers is log normal.
Yeah, I'm coming to that. Okay. Yes, that's exactly what I'm doing. Hold your question for 1 second, you will see the data. That's absolutely, you just saw through my slides. Okay. So here is the experiment. I'll quickly give you the, so if you have a gapped bilayer graphene, and this is at 20 millikelvin temperature, conductance is in the unit of E squared by H. If you simply make the Fermi energy go from here to here, you see this standard conductance goes, when the Fermi energy is at the gap, at the right in the middle, you will see this dip in the conduction, okay? Okay, what experiment we do here is that we fix the Fermi energy at various points in space, in different positions, and we essentially look at a tiny region around that. So if you take a look at this region here, and you see the conduction is taking place with some form of reproducible fluctuations. You can see these fluctuations, there are several runs on top of each other, which means that these are not standard noise, is essentially reproducible fluctuations in the conductance as the Fermi energy is going across a series of localized states. Yeah. You can see how reproducible they are. There are 8 sweeps of gate voltage along this region, and conduction is exactly on top of each other in every sweep. Okay? Now, question if it asked. If I take the conduction, when the Fermi energy is deep into the conduction band or valence band, and I do the same thing, that is, I take the statistics of the fluctuations, you can see the fluctuation is essentially Gaussian in nature. That is, the conduction is distributed, the probability of conductance is roughly, you can see this is a rough normal distribution of G in the metallic or weakly localized regime. However, if we look at the strongly insulating regime, where there is a gap in the, where the Fermi energy is deep into the gap, now the statistics of conductance as a function of G is no longer simple Gaussian, it's a log normal distribution. I don't know, is this something that you asked for? Yes. That's, yeah. It's a transmission oriented, yeah, transmission probability that is going to get added up. Maybe we can, yeah, we can go ahead. So what we do here is now once we have this, we look at the distribution, the width and the mean of the log G. You can see in log G it becomes roughly normal, and we compute what is the ratio that R log G is nothing but the variance divided by the mean square is ask the question whether R log G changes as a function of system size. That was our goal to start with. You can see as when you go deep into the metallic regime or when the gap is very small, eventually the transport, the conductance fluctuation leads to 1 E squared by H, which is nothing but the manifestation of what you call the universal conductance fluctuations. In the localized regime, large number of samples, different lengths whatsoever, you can see exactly the similar kind of behavior, which is strongly log normal distribution of the conductance statistics. Okay? Now, the question that we wanted to ask, is it self-averaging or not? Because if it is self-averaging, then the R log G, which is the distribution width divided by mean square, should be proportional to the square of the system size. And when you have low band gap, which essentially means that the transport in bilayer graphene is, after all, a two-dimensional transport in nature, then you can see as you go to higher and higher system size, the conductance statistics actually scales as 1 over L square, means the transport is two-dimensional. But if I go to strongly insulating regime, when the gap is very large, which is high band gap regime, that's when situation changes drastically. And as you can see, that when you have the typical gap is in the order of 6. This is about 60 millielectron volt, 70 millielectron volt, 90 millielectron volt, 110, 130 millielectron volt of gap. These experiments are done all at dilution refrigerator temperature, where temperature fluctuation is very small. Essentially there is no dependence of the distribution width on the system size, and in principle, it means probably that the transport is happening predominantly along pure one-dimensional edge states. There are gaps because of bad disorder along the edge. It's not pure zigzag throughout, and as a result, we get probably non-self-averaging transport in gapped bilayer graphene. That's more or less what I wanted to say about bilayer graphene. If there's any question, otherwise I will last 15 minutes or so. I will tell you about magnetism. Yeah. Yes. Yes. The problem of doing temperature dependence in the strongly gapped region, but here in these temperature range, it doesn't give the band gap of the graphene. You start getting the band gap at slightly higher temperature. Here, because the transport is primarily dominated by a strong disorder, yeah. Well, I mean, in the metallic region, we start getting weak localization behavior. You can see here. You can see in the metallic region here, the conductance fluctuations are essentially approaching E square by H, which is the universal number. This essentially reflects universal conductance fluctuations, standard logarithmic corrections to conductivity, and so on and so forth. There's no... Which one? This one? Well, I mean, yes, it will depend on temperature and through the phase breaking length. If your temperature is becoming so high that the phase breaking length starts becoming too small compared to the system size, that's when the temperature starts affecting. But all the temperatures that we have looked up here, the phase breaking length is usually as large or as long as the system size itself. So that's why the temperature dependence is very weak in most of our experiments. Okay. Right, so after this, let me just go to the next section. Is the question that we asked after this is, well, the electronic transport is fine, that we now have edges in the ballistic edges in single layer graphene in point contacts. We have got probably edge state dominated transport in single layer. What about magnetic states along the edges? So one of the things that we did in the case of our first experiment where we looked at the point contact, we found something really interesting at that point of time. That is, this is essentially when we applied a perpendicular magnetic field in this point contact region and found that there's a huge hysteresis in the magnetic field, in the conductance. The moment a magnetic field increases, the one-dimensional conductance that we saw decreases immediately. But the back and forth direction of magnetic field is not on top of each other, but it gives you a hysteretic nature. Very similar to what happens in the case of a ferromagnet or a frozen magnetic system, okay? We were not too surprised by that because there were already evidences in the literature. Probably the edges of graphene are magnetically ordered phase. We didn't know what the origin is. Probably origin is Coulomb interaction, but we didn't want to go too much in that direction. In the case of bilayer graphene situation, this is much less clear. There is not too many experiments which show what kind of magnetic state the bilayer graphene edges are at. Probably still an open theoretical problem, if I understand. And if you see our experiment, this is an ongoing work, and I just quickly flash a slide on this. You can see this is at 0 band gap, which is why the conductance is much larger. This is at large band gap, 0.6. This is about 60 millielectron volt and 70 millielectron volt. As a result, the conductance is much lower. And if I do a magnetic field sweeps, you can see strong hysteresis generating in the conductance versus magnetic field result. And these hystereses are particularly strong close to the zero magnetic field region, again, similar to what we have seen in the case of single layer graphene. Open question, this is an ongoing work. I just wanted to flash the slide just in case someone has an idea. But the work that we did in detail afterwards was probably this one. That is, we asked the question whether the third form of boundary in graphene, that is a grain boundary, has got a magnetic structure in it. So this is something which is a thesis work of Kimberly Shea, which is, who's going to submit maybe in 2 or 3 months. We can now grow graphene with extremely well-controlled grain boundary structure. That means you have 2 grains of graphene, you can merge them at our will, with just a single grain boundary. And we can then make a device. This is a typical grain boundary that you see in a tunneling, in a transmission electron microscope. And we can make a device exactly across the grain boundary so that we can measure the electrical properties of the grain boundary both across the grain boundary as well as within the single grain region where there is no boundary. Okay? And then compare. If you see Raman spectroscopy, you can see this is the grain boundary region where the disorder peak is very strong, but this is a single grain region where the disorder peak is low, showing that there are 2 structurally different regions in graphene. Okay? Right. So the question is, can graphene grain boundary be magnetic in nature? And if it is, then how do you look at it? So this is typically a graphene grain region, this particular device, where there are 2 traces. One is across the grain boundary, which is the red one. And if I do the same experiment with a single grain region, which is this, the conduction is more mobile. So the mobility of electrons across the grain boundary is slightly lower than the mobility of electron within the single grain. It's very interesting is that the grain boundary width is just about 2 nanometer, 2 to 5 nanometer. And the system size is nearly about, this is about 10 micrometer. Even a single 2 nanometer region makes this much of difference in the electron mobility. Okay, interesting part is we did magnetotransport and we looked at the phase breaking length of the electrons inside the grain boundary and within the single grain. You can see the region, the single grain, the phase breaking length of electrons is usually significantly higher than the region of by low field magnetotransport. We look at weak localization behavior, we fit the weak localization behavior with standard Hikami formula and get the phase breaking length from there. Yeah. I have the data, but I didn't want to put it here, it's raw data. So the phase breaking length is usually longer in the single grain region than the grain boundary region. So naturally, L5, the entire sample is sitting on the same electrostatic environment, on the same substrate. The fact that the phase breaking length is shorter naturally raises the question whether there are local moments that are developing in the system with the grain boundary, and hence whether there are other kind of magnetic ordering that is coming in. It's usually extremely difficult to probe these systems with standard magnetic probing. You cannot do magnetic force microscopy or other things. Probably diamond vacancies, nitrogen vacancies, diamonds is the probably only way one can look at that individual magnetic moment along the grain boundary. We are really talking about a series of magnetic moments along the length. Okay? So the question that we asked, whether can we probe if there is magnetism, then there is a breakdown of time reversal symmetry. Can you probe time reversal symmetry in these systems? And one of the ways to probe time reversal symmetry directly is universal conductance fluctuations, as I told you earlier. Let me tell you again the basic idea behind the system, behind this experiment. So if I take a standard graphene and I take a look at the electrical characteristic, this is electrical characteristics of graphene, and I look at its resistance as a function of time, you can see the resistance is strongly fluctuating as a function of time at the Dirac point. As you go to larger electron density region, this is hole density, this is electron density, larger electron hole density region, the fluctuations decreases, the magnitude of fluctuation decreases, and this is what we call noise in time domain, okay? Now, what is noise? At the end of the day, the noise is nothing but an autocorrelation function of 2 different paths. And in the quantum regime, in the quantum interference regime, this is, if you look at the standard propagator framework is nothing but a cross correlation between two paths of electron that goes from this from the source to the drain. Okay, I can essentially categorize all these pairs of paths in two ways. Okay, and one is called a diffusion, which goes from here to here, and essentially at every point they are moving in the same sense, or a Couperon. I'm sure this is something which is relatively, people here will be well aware of. So the Couperons, of course, there are regions which are in opposite sense, so that when I apply a magnetic field on this Couperons essentially vanish, because when I apply a magnetic field, the Couperon contribution vanishes because the phase difference that is generated in different Couperon paths essentially interfere destructively and eventually average out. As a result, what happens, the universal conductance fluctuations reduces exactly by a factor of 2 when you apply a magnetic field which is larger than the phase breaking length. So this is a unique property of universal conductance fluctuations in any disordered systems. And we wanted to use this unique property to understand whether time reversal symmetry is maintained in our disordered graphene grain boundary. Okay, how do you do this experiment? Oh, by the way, this factor of 2 reduction can be obtained in many ways. This is a random matrix kind of a model as well. You can see that when you have B greater than B phi, the system goes from the the orthogonal symmetry class to unitary symmetry class, leading to exactly a factor of 2 reduction in the magnetic field, as a function of magnetic field. Okay, the experimental probe for us is nothing but the noise, and I calculate the variance of noise from simple experimental data like this. I take an experiment, I integrate over the time taken over the entire experiment, and compute this term n as a function of magnetic field. If I do so, then it turns out to be something like this. This is within the single grain of my graphene. This transport, you can see, if I take the same, compute the value of n as a function of b at this point and at this point here, you can see exactly a factor of 2 reduction in the magnitude of n as you change the magnetic field from in either direction. Okay? So that's essentially because the Couperon contribution to the universal conductance fluctuation has been removed and only the diffusion contribution has remained. And this change has happened over the scale of the phase breaking length itself, B phi, and this number L phi is completely consistent with the number that we get from the Magneto-transport measurements. Okay? So have a look at this. This is true for whether you take the conductance, whole dominated conductance, or you can see here this is electron. Again, the change in the universal conductance fluctuation, or the conductance fluctuation magnitude, is exactly a factor of 2 different in the two sides. Situation changes completely if you have, if you do the same experiment on the same device, but across the grain boundary. Here is the result. You can see if I take at the Dirac point the noise as a function of magnetic field, there is a factor of 2 reduction, but note something very interesting. That's here the noise reduction occurs at a slightly wider magnetic field because the phase breaking length is slightly shorter at the grain boundary. That's why the magnetic field scale at which the noise decreases by a factor of 2 is slightly larger. But the moment you go to higher density, like 90 volts, over here, the reduction magnitude is significantly smaller. This is taken at 4.5 Kelvin. And this essentially is the reduction factor, means that now the noise is no longer entirely dominated, the absence of time reversal symmetry is no longer due to the magnetic field anymore. It has already removed partially, this is partially here, because it has not gone to 2, but it has gone to 1.5. I'm going to show you more data here. The time reversal symmetry probably was partially removed already from the system, and hence magnetic field has reduced only a fraction and not entirely from 2 to 1. A little bit more on this. So here is a consolidation of all data. So if I take a single layer graphene here, this one is single layer, if I take the single grain region, I'm sorry, you can see as you change the density in either side, the reduction factor is 2 no matter what density you are at. But if I take the part which is across the grain boundary, if you increase the density, the reduction factor is 2 at the Dirac point, but reduces continuously on either side as you dope the system more and more with electron or hole. If I go to slightly lower temperature, this is the one which I wanted to flash at last. You can see this is at 284 millikelvin. You can see along the single grain region, there is a pure reduction of 2, but across the grain boundary, there is no factor of 2 reduction at all, means probably the system had already lost its time reversal symmetry from some reason. Yeah, sure. Yeah.
Why don't the electrons in a single grain go and collide with the magnetic moments of the grain boundary and then come back?
Oh, no, but that's because you are restricting your current flow is always across the grain boundary. So there's a 4-probe transport. Imagine the 4-probe transport with the grain boundary at the middle.
No, I'm thinking about the case when you're going through a single grain.
Yeah, that's right. Oh, that's because your current is always, there's no non-local transport. This is a local transport. Your current path does not include the grain boundary at all. Yeah, but correct. But the majority of diffusion will happen, the voltage drop, the region of voltage drop is far away from the grain boundary. And if you take the exponential in a non-local transport, it's usually much smaller. In this, but at lower temperature, the absence of time reversal symmetry is almost complete. Okay, so that's there has been some calculations by my colleague Manish Jain in the department. If you look at again, the question, we do not know the answer to the problem here, why the time reversal symmetry across the grain boundary seems to be absent spontaneously at very low temperature. I'm down with my last slide here. But tunneling electron microscopy shows there are different types of defects that can be present in the system. One of the defects possible is this pentagon-octagon. You really need to see, like transmission electron microscopist, to understand what the nature of defects are. I'm not an electron microscopic person, but I was told that you can actually look at these systems in the defects in these ways. There's a pentagon-octagon pair, and there are these standard heptagon-pentagon Stonewell's defects. It turns out that the calculation has shown that indeed the grain boundaries with the pentagon-octagon pair can develop magnetic moment, and these magnetic moments can be up to about 0.8 per defect. A question, of course, remains whether these defects are indeed magnetic, or the fact that the time reversal symmetry seems to be breaking down as you increase the charge density in the system probably means that there are moments which can be continuing to communicate with each other through either RKKY interaction or something else, leading to some form of frozen magnetism, because time reversal symmetry requires, or breaking of time reversal symmetry requires frozen magnetism of some form as one possibility. But in any case, this is an open problem, and we are still trying to understand where does the time reversal symmetry breaking can come from. So that's more or less it. I wanted to stop here. This is the conclusion. We look at different parts of, or different kinds of physics that can emerge at the boundary of graphene. In a single layer graphene, we have been able to make ballistic transport at the point contacts. In the bilayer graphene, we have detected edge transport, and resolving probably a perplexing question whether gapped bilayer graphene is indeed a two-dimensional material or a one-dimensional material. It looks like the gapped bilayer graphene is more a one-dimensional conducting system rather than a two-dimensional one, which was counterintuitive to say, and probably connected to the topological nature. And the third is the boundary of graphene. It looks like even single and bilayer graphene has got non-trivial magnetic structure, but our experiment with the grain boundary appears that at very low temperature, remember, all these features go away above 4 to 5 Kelvin, but below 4 Kelvin, up down to 20 millikelvin, it seems that the time reversal symmetry in the system seems to be absent or suppressed. Whether it is because of interaction effect at the grain boundary or is because of the defect structure of non-trivial nature is still an open question. Thank you for your attention.